Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, it's a great pleasure to welcome Partha Ranganathan. Partha got his PhD at Rice University, and he's currently a principal research scientist at HP Labs. Partha's been doing work on computer architecture and parallel processing, and as you'll see in his talk, he's been looking a lot at issues around performance, power, and manageability. Partha's also leading a new project called Blades++ at HP Labs, investigating next-generation system architecture for enterprise environments. And so if you get a chance to talk to him, you can talk a little bit about that. Anyway, it's a great pleasure to welcome Partha. And I just want to mention his schedule. There's still some time in his schedule this afternoon. So if you want to spend some time talking to him, we can probably arrange it. So just talk to me after the talk. Thanks.
Okay, sounds good. Okay, so, well, the title kind of talks about itself. And as Ben mentioned, my group looks at a couple of different things. One is the SmartPower project, where we look at power management across the spectrum of devices, all the way from handhelds to data centers, and then the Blades++ project. And today what I really want to do is to focus more on the SmartPower project. And even there, basically, the agenda is kind of out here. So what I really want to do is to oh, this pointer is pretty faint here. So what I really want to do is to talk a little bit about what is the power management challenge, what are the problems we are trying to solve. And I'm going to focus on two specific solutions in great detail, and then I'm going to try and give you a sense of some of the other work. And hopefully, if I have time, I'll kind of talk about our efforts in tying this all things together and kind of some of the work we have done in taxonomizing various approaches and so on. Okay, so let's think about why is power important. I put up a couple of cartoons. Well, there's one, and then there's your data center blowing up. But more importantly, I mean, these things give you your funny punchline. But what's interesting is both of these cartoons were found from a quick web search. I won't tell you which search company I used. But they're quick web search looking for the terms data center, power. And it's kind of funny when you have things in the public domain in the popular cartoon strips about power management. And the point basically is power management is increasingly a bottleneck, irrespective of whether you look at processors, servers, supercomputers, data centers, or whether you look at the mobile market, the handheld market, the data center market, enterprise market. And so when we start thinking about why is power important, we tend to think about it along two axes. The first one is the average power axis, and there basically the key point is how much electricity do you consume. And so if you think about mobile devices, pretty much everyone here has had problems with recharging things. And so this is obviously going to get worse with convergence and smaller form factors. So this particular thing basically has a whole bunch of functionality, and I always keep wanting more. And as I start adding more and more stuff, the battery life gets to be pretty interesting. And so that's obviously an important issue. But what's interesting is for tethered devices, the electricity cost is getting to be an important issue as well. And San Francisco Chronicle had an article about Google's data center power, and that was running in the hundreds of millions of dollars per year. And so this gets to be pretty interesting very soon. And then there's the second aspect of power consumption, which is the environmental friendliness. And so this is basically numbers, 22 million gigajoules, 4 million tons of carbon dioxide. This is just for the annual consumption for computation just in the US alone. And then obviously that's getting to be a big issue. In fact, I'm in conversation with DOE, where they're basically looking at an Energy Star rating for servers, and we've been helping influence what that metric ought to be. And it's always funny when people try to legalize interestingly silly things. So.
Can you help with the scale? I'm sorry, I'm from the handheld space, but 1,000 racks, is that a common data center? Are there thousands of those in the U.S. or?
This 1,000 racks is basically, if you look at Oracle's data center in Austin, for example, so 1,000 racks is pretty large, but it depends on also what you have in your racks. And this is assuming 8 kilowatt racks, and you'll get a sense of this as we go along. So again, Google, Oracle. Actually, I was down at Microsoft's data center back locally here as well, and so these are all kind of good-sized data centers. But it's going to be a problem irrespective of whether you have a departmental data center or an enterprise data center.
Just in labs here, Redmond, there's 7,000 racks.
They're not 8 kW racks, but there's 7,000 racks in labs today.
There you go. You got a data point right there. So do the math there. He just said 28 million? No. But anyway, so the second axis of power is basically the peak power. And so when we talk about peak power, this is basically thermal issues. And a lot of time, especially in the enterprise environment, this is what people worry about. Basically the power delivery, the packaging, and cooling. And so if you look at various data here, I'm just going to focus on this particular set of pictures here. The blue line is, let's focus on the red line. That's the energy consumed by your servers. And the blue-green line is the energy in the air conditioners. And the takeaway point is, as you go to the higher end, for every watt of power you consume in your servers, you're going to need an additional watt, or even sometimes an additional couple of watts to extract the heat here. So going back to the Google data center, $100 million in server electricity, $200 million in the air conditioner electricity. So it's kind of a vicious cycle in itself. And then there's a whole bunch of temperature noise issues. This is particularly important for our European customers, where they worry more about noise, but this is getting to be important everywhere else as well. And finally, there's a whole bunch of soft metrics like compaction, density, and reliability. So if you were to think about dense blade servers, for example, thermal issues get to be increasingly interesting. Reliability. Most people know that when the temperature goes over a certain point, things are going to shut off. But what is also interesting is that when you operate your server, for example, if you operate at more than 10 degrees Celsius over the default operational temperature, it's been documented, this is actually data from Uptime Institute, that you have a 50% degradation in your reliability, and same thing with hard disks and so on. So basically, there's going to be a lot of soft issues in terms of peak power and so on. So, well, then the obvious question is, well, power management and the associated problems are really not new. There's been tons of work done there. So, and this is basically kind of a quick summary of all the work that's gone on here. I'm not going to go into more detail. I actually teach a guest course on power management at Stanford, and this takes a whole quarter. So my goal is not to kind of give you a tutorial on what's been done, but the point is to emphasize that people have basically looked at it at the circuits level, at the architecture level, at the operating system level, application level. So there's tons of work done. So the logical question is, well, why the heck are you working on it, right? So let's kind of take a step back and look at what are the goals that we want. And there's actually a very interesting paper from IBM, and if anyone is interested in power management, that's a very classic paper I'd encourage you to read. And it kind of talks about the holy grail of mobile computing, which is human-powered wearable computing. And it actually talks about energy sources from as silly things like body heat to things like walking and so on. But even if you aren't worried about this, let's look at solar-powered. And so if you look at solar power, and this is for California, not Seattle, so you're assuming quite a bit of sun here. And even there, you basically look at the amount of power that you can generate. It's in the order of milliwatts, and you look at a typical handheld or a typical laptop. Essentially, what you're looking at is you need huge amount of improvement in where we are to where we want to go. And so the holy grail is quite a bit far away. Same thing with if you look at tether devices. So this is actually a picture from a keynote that was given about blade servers maybe a year or a couple of years back. And what it talks about is this is your typical traditional server rack, and it says somewhere about 8 kilowatts. But as you kind of go to more denser servers and more blade servers, you're looking at easily about 55 kilowatts per rack. So that's almost a factor of 10 increase from 6 kilowatts to 60 kilowatts. And so essentially, if this continues, if you look at the amount of cooling that you need in terms of BTU per hour, you're now coming to a place where you're literally talking about liquid cooling in the data center. So that's kind of getting to be a problem. And this is actually a picture from our conversations with several customers. And what each of these stars are is actually a customer data center. Going back to what you were asking about, what is a customer data center? So you have the size of the data center here, and you can see that there's a whole spectrum of sizes here. And you have the density of data centers here in terms of watts per square foot. And the point to take away from this picture, there's a whole bunch of interesting data here, is that most of current customers are operating somewhere around this range. And there's a few people here who operate around 5 kilowatts per rack. And there are some people, including there's our experimental data center, our labs data center here, that operate around 10 to 20 kilowatts per rack here. But when you're talking about 55 kilowatts per rack, you're going to get a lot of pushback from customers about the infrastructure needed to support that. And so this is getting to be an interesting problem. And so this is basically just summarizing both of that. And it says essentially you need, once again, orders of magnitude improvement.
So what's the benefit of putting that much in a single rack?
How do you bin it instead of spreading that out among multiple racks? Because I'm looking at your chart there in the watts per square foot, and I'm building a lab at 250 watts a square foot, and I'm allocating 20 square feet per rack. At 250 watts a square foot, you're up in that top range.
Yeah.
And so you're looking at probably 50 to 60 square feet per rack to get those kind of densities. So what's the benefit of having a single rack with 55 kW in it instead of having 10 racks with 5 kW in it?
Very good question. So basically, if this density is killing us in terms of what the facilities guys are telling us, so why the heck are the IT guys going towards more and more density? And there's a couple of trends, and I'm not actually spending a lot of time on that. But if you look at one of the trends, I know Microsoft, several people are worried about, is a multi-core processor. So basically, if you look at the fact that Moore's law gives you more and more transistors, you're starting to put more and more stuff in a single socket. So there's going to be a lot of compaction at that level. And if you look at processor power budgets, they are kind of going up the roof. The second thing with blade servers, why do people like blade servers when you can get a lot of things similarly functional with rack-mounted servers? The interesting issues has to do with the manageability. So if I were to draw a pie chart of all the costs in the data center, the biggest chunk of that pie chart has to do with the operational aspects of managing a data center. And so by being able to compact things into a blade form factor where I reduce cabling, where I provide a single unified management abstraction, it dramatically reduces the cost. And so people are willing to pay a little bit more in terms of density. And so that's kind of the tension. You're going to have compaction because of the technology trends, because of the operational trends, and then you're going to have some pushback because of the power and thermal density trends. And ideally, if I'm able to solve that, and I promise 10x at the end of the talk, basically then you can start facilitating some of this as well. So any other questions here? Okay, so the question basically, is there anything to be done? And obviously, I wouldn't be here if there wasn't. And so that's kind of, so what we do at the SmartPower project at HP Labs is to systematically understand the power management problem. And later on, maybe if I have time, I'll kind of talk about some of the interesting taxonomies that come from the systematic analysis. And there's a whole host of solutions that we have, of which I'm going to focus on a few. And even though I'm going to focus on the more visible part in some respect, the power-aware system and solution design, there's a lot of work that we have done under power measurement, monitoring, kind of the plumbing. But this is actually, there's a lot of innovation that went in terms of understanding the tools, the metrics, the benchmarks, the frameworks. And again, I'm not going to have time to go into that, but I'll try and give you guys a sense of that if anyone of you is interested in following up. Okay, so and since I intend to leave this slide deck with you guys, and since I intend to also kind of cover high-level goals, what I did was to put together a bunch of list of papers that you could look at. And so the first one has to do with energy-aware user interfaces, reducing display and communication power. And it looks like I have an older version of the slide deck here. So the best paper to look at is an IEEE computer cover feature that came up in March of this year. And that has a very good summary of what we do. So let's start thinking about energy-aware user interfaces, right? So I kind of pointed to this handheld that I had. And if you look at the key sources of battery power consumption, the display, the processor, the wireless are probably the three most dominant. And the display power takes up quite a bit of power. If you look at the battery life, I have data here which says 50 to 60%. But depending on the system, you can have anywhere from 30 to 70%. And so previous approaches to turning off the display power have predominantly focused on turning off the entire display. So you have pesky screensavers that come in and blank the screen when you most want to use it. Or you could essentially buy a laptop, for example, with a 13-inch display if you are a road warrior, and that gives you longer battery lives and so on. And so when we started this research, our goal was, well, both are really not quite good. So can I do something better? And so we came up with this notion of energy adaptive displays. And the fundamental idea is fairly simple. It's basically, can I come up with a display subsystem where the display power consumption was matched to the screen content for the user or the task? Or the idea is basically, given what the user is using, can I match my energy to exactly expend energy just on what's going on at that point. And so there's a couple of challenges there. One having to do with first understanding how do people typically use their screens, and then the hardware and software design. And when we're talking about displays, we are now actually mucking around with the user interface aspects of the interaction. And so we want to make sure that we do it in a way that the user experience doesn't get compromised. And I'll talk about that as well. Okay, so let's first focus on understanding screen usage. And so what I have here is basically a picture from a user study that we conducted of 20 different users. And what I have on the x-axis here is the percentage of screen area used. And on the y-axis is the cumulative number of samples. So the way to read this is each graph is one user. Let's focus on this solid line, which is the average. And so what this says is 50% of the time, on average, less than 45% of, actually it's the other way. So about 45% of the time, on average, less than 50% of the screen area is used. So the point is, on average, across all our different users, less than about 60% of the total screen area was used. And this is just the size of the screen. But if you look at color, resolution, refresh rate, in general, all the full functionality of the display was not being used all the time. But if you look at your display power consumption, in most displays, it's one big, solid, flat line, right? So I see a couple of people with laptops here, and I'm willing to bet that if you were to go look at what they're doing with their laptops, they're probably using Microsoft Word, white screen, white background, black text, and they're probably using, if you look at the actual pixels that they're using, it's going to be a much smaller fraction. I see him smiling, so at least I have one person doing that right here. So, but anyway, so and so we have a whole paper which talks about why this happens, and it has to go back with the content the user cares about and how they want to do stuff there. And so that's kind of the goal here. Question?
I think you're right that color is essentially never that essential, but try giving away a black and white laptop.
Sure.
Not on a black and white desktop.
Sure. So the point is, again, that's the whole point. That's why I called it energy adaptive displays. Can I have the low power of a black and white display, but still be able to promise color functionality when the user needs it? And you'll find that exactly what we do here. So you'll notice that there is a black and white screen here, but it is actually a color screen here. So the point, again, is to be able to selectively turn off properties of individual pixels in terms of brightness, in terms of color emissiveness, and a whole bunch of other stuff, and be able to do it from a power point of view. So in terms of our prototype, we focus mainly on organic light-emitting diodes, OLED displays. And OLEDs have this nice property where you have a power consumption based on the pixel value, and different colors have different power consumptions and so on. And they are kind of starting to get there. It says expected in Handhelds 2006. And I believe there is a handheld that's actually in productization which uses handhelds. And then there's the software aspect, which is basically once you have a hardware display screen which can control your power, how do I now control it in software? And that basically means you want to have user interfaces where you selectively turn off portions here. And this is a very silly example where this Emacs window is your window of focus, and you kind of dim the background, darken the background, make the background black and white. And the last case is where you actually go to greenscale. And it actually turns out for the particular OLED chemistry we were looking at, greenscale was actually a more energy efficient color combination than the rest of the stuff. And so the point here with this picture is just to show that this all works. And so here is a typical user trace based on the user study that I talked about. This shows your window of focus and how it varies. And this shows your power consumption. And your yellow line is basically with your base LCD where it actually varies about 1.5% or so here. And then you actually have the solid blue line where you can see that the power consumption now actually tracks what the user is doing with the screen. And so the idea basically is if the user needs color, you kind of go to one of the spikes, and if the user needs something else, you go to one of the troughs here. Okay? Okay. So the question basically is, well, that was kind of a simple proof of concept, and we said, well, all of this works. Let's kind of start thinking about more complicated user interfaces. Yeah.
Was that some kind of idealization? How did you know to switch? To sort of highlight one thing or darken another thing? Was the user telling you to do that? Or?
Just hang on. We are going to. That's why we have fancy flash demos here. Okay, so kind of again, so Ben is absolutely right. That was kind of a very simple proof of concept exercise, and there is a whole bunch of science to how do you do it and not annoy people, right? We have all seen paper clips that wake up and tell us to do things at the least opportune times. So this is kind of the simplest one is basically whenever you have a window of focus, you kind of dim the screen. That's fairly straightforward. That's the example I talked about. Let's look at this is Pocket PC Outlook. That's the same Outlook screen that you see on your thing. All of this is Flash, so we didn't muck around with the source code for fear of contamination, right? So, but the point basically is, so this is your default Pocket PC screen. It's hard to see what we're talking about here, but there's a small battery icon that says 2 hours, and that's kind of the power consumption for the displays here. And so the idea is basically you start reading portions of the screen, and you can kind of dim portions of the screen, and we basically have a user interface that kind of does that at the level of individual messages. So that's one option. So another option, oh, and I forgot to mention that if you look at the battery icon, okay, I guess if you look at the battery icon, you go from 2 hours in my screen it says 5 hours. So a factor of 3 improvement there. So if you look at Acrobat Reader, so this is basically you can read something this way, or you can kind of start dimming portions of the screen and read things this way. So the idea is basically you have a moving window of light that tracks what you're doing. Now this is where it gets interesting. Just hang on for a second. So this is where it gets interesting is we basically now started conducting user tests where we hired an external agency. They picked people off the street and then had these user tests where they said, would you like an interface where you read something this way, or would you like to read something this way, right? And what ended up happening was 95% of our users responded saying that they would prefer this new interface over the old interface. And this was even before we told them that you just have a factor of 4 improvement in your battery life, right? And so that was very strange to us, and we said, why is that the case? And a lot of people came back saying, well, you know, it's kind of emphasizing the area we care about. One person actually mentioned it's kind of like a bookmark. I can kind of talk to someone else and come back and figure out where I left off and so on. But the meta trend here was that we were de-emphasizing portions of the screen to save power from a battery life perspective. And the users ended up thinking that we were emphasizing areas that they cared about from a user interface point of view. And of course, we tell people that was the goal all along, right? But the point again is now when we show people the new user interface and tell them about the battery life benefits, it's pretty much a no-brainer to kind of start thinking about this notion of energy-aware user interfaces. And then the final example is Windows Media Player. The battery icon says 2 hours here. So you went into something that's more green, literally, and that's 6 hours. And so the interesting part is if you look at what we have here, I actually have like a graphics equalizer. I actually have like the information about the tracks as compared to the old one. So I actually have more information in the new screen. But what I've done is I've turned off a lot of the pixels. I've used energy efficient colors and so on. And that gives me a battery life of 6 hours. This is my screensaver, and it looks pretty awful with the projector resolution. But I have a demo on my handheld that you guys can see if you want. And so that you can see that the battery life is about 40 hours or so. And basically the point is you've essentially turned off all the pixels, focused on the content the user cares about, the buttons and things of that kind. And then so you can actually go quite a bit there. And then so again, and I just have the usual screensavers come up after 30 seconds just to illustrate the point that that one loses content. You can get a lot of the power savings without really losing content. So there's a whole bunch of things you can do with this thing. So I kind of talk about the spatial and temporal. And again, we have a couple of papers illustrating how you can design user interfaces. So there's, again, in my demo, there's a bunch of interfaces that did not work as well. So this is research. So we got to show some negative results as well. And one of my most favorite things that did not work was this amazing, incredible shrinking window. And so we had this window where if the user did not use it for a while, it would become smaller and smaller. And for some reason, nobody really liked that. So. But anyway, the point is, again, you can kind of think about a whole bunch of things, and this actually gives you more screenshots, and it talks about the ones with high acceptance, medium acceptance, and low acceptance. And one thing we found was that making the screen completely dark was unacceptable. Several people mentioned that it made them claustrophobic, and it was very dark for their taste, and so on. And so so there's a lot of takeaways there. And again, like Ben pointed out, the science is basically in the insights that go into codifying these energy-aware user interfaces. And we have actually one of the artifacts that came out of this work is a set of energy-aware design guidelines. So the idea is basically if you were to have it energy compliant as certified by HP, if the developers were to follow a certain set of guidelines, we could kind of give them pretty good guarantees that the users would like it, and it would also save some benefits. And there's a bunch of intuitive and interesting things there. So that's kind of the bottom line. You can actually save anywhere from a factor of 2 to 20 in terms of the display power, and the user acceptance was quite high, and then it has sub-qualifiers on when it was high and when it was low. And what was very interesting was that for the first time, we actually now have something that's a win-win, where you basically can reduce energy and have better user interfaces as well. And that was, in some respects, the most surprising conclusion that we really hadn't anticipated when we went into this study. Very briefly, just kind of some of the follow-on things here. We looked at very simple design rules, and again, those are typified here: on-off rule, grayness rule, color rule. But you can kind of extend this in several interesting ways. And then a common question I get asked is, well, this assumed OLEDs, which is an emissive display, doesn't have a backlight. What happens if you have an LCD display with a single backlight that's taking up all the power? And so we actually had a solution that works for that as well. And it is a little bit more challenging, but you could think about hybrid backlights where you have 7 backlights that illuminate it in several interesting ways, and there's a bunch of things you could do there. But another interesting thing that I really like is the notion of having multiple displays. So basically divide your screen up into a high power, high color, high everything, high energy display, and a low power, low color, low everything display. And so the idea is, just as we had insights on how do you selectively dim portions of the screen, you can pretty much translate all those insights. It's a little bit harder, but we've done that in terms of how you can actually selectively use these 2 displays and still not compromise user interfaces. And this gets very interesting when you're thinking about laptops, for example, where you can start imagining a small taskbar, alert bar kind of things, and so on. So there's a whole bunch of work there. And finally, I talked about content, and I talked about adapting the energy based on the content. You could go one step further and start thinking about the intent, and start thinking about adapting energy based on the intent. And that's the whole idea behind these multimodal interfaces, where in the first case you said, well, you have mail as a notification. Can I dim all the white portions, or can I put that in a smaller low power display? But essentially the intent is mail notification, and you could do that very well with a blinking LED light there. And that's 100 times lower power than anything that you have with the display power and so on. And so you can start thinking about more energy efficient alternatives, looking at the intent of the communication there. I had a question there. So,
you know how the modulation of the OLEDs are accomplished? Is it analog or pulse width?
So we actually worked with Kodak on their OLED stuff, and I believe we had drivers that were more at, let me think about this. So we basically had an OLED display panel. They changed the driver. So actually I don't know. So all I know is they changed the drivers, and I don't know enough about.
If it was analog, you could conceivably save a lot of power there.
Okay. So, but again, I think the key is we actually have a prototype in the lab which I didn't bring in because it's got wires and everything running out. But the point is, we worked with Kodak, got an OLED display panel. They just had to change their device's circuitry. So it might actually be analog. I don't know. So, and they changed their device's circuitry, and then we changed the firmware and the UI layer on top of that, and then we measured the power. And so the numbers I have are very closely matched with what we got there.
So are OLED displays really going to displace LCDs at some point, or what are the?
You want to get me into religion here, don't you? The point is,
looking forward to getting one. Actually,
so OLED displays, 4 years back, 5 years back, they were the next big thing, and I believe they still are. So, but the point is, they have made quite a bit of inroad in several other domains that we expected them to. So usually, when I first gave this talk 4 years back, I had this adoption roadmap, and we talked about car displays and small cell phones and handhelds and laptops, and it was very clear that laptops was kind of quite a bit in the future, and it still is. But the rest of the roadmap has been working out pretty well, and so you see a lot of OLED displays. The problem is LCDs are also improving. But the point is, what we've talked about, the notion of energy adaptive displays or energy adaptive user interfaces, are just we used OLEDs because it was the simplest way to demonstrate it, but you could pretty much get all these benefits using any display technology. You just have to work harder to understand how to provide adaptivity. So that's an interesting question, but not quite directly tied in with what we're talking about. Yes, sir.
You have ignored electronic ink after now. You believe it's bogus, you believe black and white, one cell, or why, or you just have so many minutes in the hour.
Doesn't really matter. Again, we have looked at e-ink displays and all those stuff, and they come up with a bunch of interesting things. They start off with a fairly low power base. So the motivation I talked about with displays taking 70% of the power is not as prevalent there. But again, if you want to use some of these techniques on top of that, we have several patents which talk about how do you use bistable e-ink displays, all those kind of things. And basically, there you have to kind of follow a CMOS-like model, and you have to optimize transitions as optimizing individual pixels. And so again, the concept is similar. The algorithms get changed quite a bit. But really, as I said, same answer as Ben. Interesting question, but not related to the point I'm trying to make here. So, and again, I'm not a display expert, so I'm not going to get into that religion, because I've talked to enough display guys to realize that it's a vat of, what's the thing, can of worms, whatever. Okay, any other questions?
You mentioned just really quickly before what the 3 biggest power consumers were on a small device. And you said display, I think you said processor, and what was the other one?
Wireless.
Wireless.
Yeah.
Radio.
So again, rule of thumb. it really changes because you have just a whole spectrum of devices. I mean, if you have something like an iPod with more storage and stuff like that, that gets into the picture as well. But again, for typical cell phone, handheld, those kind of things. Okay, so talking about wireless, so basically this notion of adaptivity based on what the user wants can be extended in a very straightforward manner to wireless. And we have a whole paper on this, so I'm not going to go into detail here. But the idea is if you look at 802.11, and if you look at the wireless power, 90% of the power is spent in your idle mode. And a big chunk of that idle mode power is spent in these power spikes where you're listening for the beacons, right? And right now, the 802.11 protocol sets this to be 100 milliseconds. And so this idea was a relatively straightforward one where we basically said, can we expose the higher level application requirements down to the physical layer? So for example, I have this particular device right now. Right now, if I had 802.11, it's still going to be communicating every 100 milliseconds. Can it realize that the only major application that I probably care about now is email? And can it adaptively scale that beacon interval? So from 100 milliseconds to say 1 second to say 1 minute. And by doing that, reduce the frequency of spikes there. And it turns out that you could do that and you could get 90% savings in power, which is, I mean, it's just simple math there. But the point again is that when we did these user tests, we had people having email with and without this optimization turned on, and we had people kind of blindfolded and say, pick the one that you think has the energy optimization turned on. And 1 minute, 1 second delays in email, it's in the noise. Most people can live without email for a minute or so. And I knew I was going to get in trouble there. But the point is basically, as long as you have user experience issues tied in with what they expect from the application, this thing is reasonable.
1 second, 1 minute beacon is only good if your access point can buffer that much too, right? This is the power save mode. You can't just sleep for 1 minute.
Fair enough. The paper actually talks into more detail on how all of this works. But the key point to leverage is that you could turn your phone off and the whole system still works. So, I mean, the whole protocol is set up to drop things, do stuff. So, but it gets into more trickier user interface issues when you start thinking about higher buffers and so on. Perfectly valid.
Yeah.
So.
What's the other application that would work with such a high duty cycle?
Correct. But again, if you go to the paper, one of the things we talked about is if you look at the workloads, email, phone calls, SMS, conferencing, there is a whole category of workloads. So again, at the end of the day, it goes back to what are the use cases that you think are going to be dominant, right? And there is a whole class of devices where the use cases have to do with listening. Fair enough. If I'm going to use my iPack as kind of an MP3 player while listening to email, then again, remember I mentioned what we are doing is to expose the high-level application requirements as included in all the subset of applications that you're running. And so if I have a MP3 player that is streaming audio live from some other service provider elsewhere, obviously this isn't the right solution, right? So
quick observation, the state-of-the-art from TI and Broadcom for wireless LAN is wireless LAN standby listening to an access point right now every 100 milliseconds is lower power than GSM. It's absolutely phenomenal how good these guys have gotten these things. So you've got a Nokia phone out there today that can listen to GSM and an access point for 125 hours continuous.
Fair enough. Fair enough. So, okay, so let me quickly switch tracks here. So we are at 11:05. So I have 25 minutes and probably 50 more slides. So I'm going to kind of accelerate. Somebody mentioned that they could listen to twice as much speed without too much trouble here. But anyway, so feel free to interrupt because I tend to speak faster as I warm up. So when things might get really fast here. But so let's kind of shift track a little bit and start looking at power-aware blade designs. I gave you one example of average power on mobile devices. I'm going to give you an example of peak power on enterprise systems. And so this is, we had a paper at ISCA a couple of months back which describes this in greater detail, and we have a couple more papers as well. So we call it the dense and smart architecture. It goes back to you need to be smart about how dense you get your blade servers. And it also makes for a funny tagline when people get it sometimes. So the point again is to look at enclosure level power management. You have an enclosure of 20 blade servers, and we want to reduce the peak power of this enclosure. And the key insight here is that if you look at current systems, they are designed for the peak utilization of an individual server. And what we did differently was to basically look at an adaptive enclosure level solution where the power budget was enforced in software, but the key idea was to focus on the long-term usage and look at the entire solution. And again, I'm going to talk about how this has some pretty dramatic potential for power savings. So let me motivate what I meant by that, right? So this is basically a picture of CPU utilization on a single server. This is actually data from one of the Apache servers on hp.com. So this is our own local server. I have time on the x-axis. I have the average CPU utilization on the y-axis. And I believe these were taken at either 1 second or 5 second intervals. I forget what. And so the point basically is that the utilization has all the periodicity that we all used to expecting. But the actual peak is dramatically different from the nameplate peak. So you end up with about 75% peak here as expected 100, and the average utilization is quite a bit lower. So now when you look at the ensemble or the collection of systems, this is 8 servers from hp.com. And so what I have here is basically the 3 web servers, the 3 application servers, and the 2 database servers. And what I have here is a new picture, which basically, again, time is on the x-axis, but on the y-axis, I accumulate the utilization of all these 8 servers. So each point here represents the sum of the corresponding points from these 8 servers. Okay? So the point here is basically what I summarize here. If you were to look at the sum of the peaks and compare it with the peak of the sums, there's a pretty dramatic difference. So what does that mean? If you look at this picture, given that you have 8 servers, you would expect the utilization to be about 800%. That's your nameplate utilization. And that corresponds to your nameplate power provisioning as well. So that's 800. The actual peak is close to 300. So that's almost a factor of 2.5 different already there. And the actual average utilization is only about 150. So that's almost a factor of 7, 6 change from the nameplate power. And that is very interesting, and that has to do with the fact that you have bursty workloads and you have non-synchronized burstiness across systems. And obviously this notion across systems is very critical, because what we are really looking at is leveraging a statistically large sample of systems where the burstiness can be spread out. So if you have 2 servers, both from CNN.com, and both of them go to spike at the same time, that's obviously not the right model here. But if you have a CNN.com server and you have a I don't know, MorganStanley.com, and then they have some differing patterns there, that's kind of the things we are looking at here. So, and so I kind of just gave you data from hp.com, but in the paper we actually talk about 9 different enterprise sites for a total of about 100, 200 odd servers. And again, the net difference between your sum of peaks and the average of your peak of sums is pretty darn high here, so anywhere from 25 to 90%. So what does this mean? What this means is this whole notion of compounded inefficiencies. So the way we look at managing power is we always look at the power budget for individual peaks. So you would essentially design your blade for your maximum nameplate power, so that's say 20 watts. And so if you had 20 watts in the blades, you would kind of multiply them, add some extra overhead for your enclosure. That's a 500 watt blade. And then you would have 500 watt enclosure, you put 4 of them, 10 of them, whatever in one rack, and then you have a 10 kilowatt rack. And then so what ends up happening is the provisioning, over provisioning gets compounded at each level. And remember what I showed in the earlier picture about the cooling cost increasing as well. And so essentially now you have cooling for this, you have over provisioning in the cooling for this, or you have over provisioning in the cooling for this, and it kind of starts adding up. So in the approach that we are talking about, we want to manage power budget for the ensemble, and we want to manage power budget for the typical case. So we could continue to use 220 watt blades, but you would now provision the enclosure for 250 watts, and you would provision your racks for about 4 kilowatts. And I'm going to argue, and I'm going to show you, that this actually saves you quite a bit of cooling costs, and as far as the end user experience is concerned, whether it's in performance and all the other metrics you're looking at, it's really not going to change that. And I'm going to use these 9 real enterprise workloads to prove that point. Question, sir?
Unless you spread the logical server across multiple boxes, what's to stop one rack melting while the other rack is freezing? Because one is at a peak and one is at a trough.
So when we get to the data center, I'll talk about that in a minute. So that's not going to happen. First of all, all of these things, even though we talk about managing cooling budget, everything is going to have a plan B, which is there's going to be a thermal sensor and things are going to shut down. So hopefully nothing will melt, unlike Dell laptops which explode, right? Okay, so here's your functional architecture. So the idea is basically you have hardware-software coordination for power control. So you essentially have your individual systems. Each system has a set of support for monitoring power and controlling power. And then this is where it gets critical. You have a management agent. I've shown it as a centralized box, but you could essentially have it be a distributed box And what it does is it measures, monitors, and predicts the power, and then it looks at all the individual blades, and then in the event that the total power is going to exceed your threshold, then it uses some kind of policy-driven control to throttle individual blades. So if the idea doesn't make sense, think of it as essentially budget management across a group of people. It's essentially the same thing. You don't kind of give everyone their maximum. You kind of have a budget across the group, and then you kind of move resources dynamically there. And sometimes you use SLA-driven, priority-driven scheduling of resources and so on, and that's essentially what we're doing here. So we actually built a prototype blade where we evaluated that, and this is that picture of that. And so the idea is basically this is your blade, and the areas in green are where we need some support. At the hardware level, we need some support at the CPU to throttle power, because you basically are saying, if anybody exceeds power budget, I need a way to bring it down. And then we needed some support at the enclosure controller, predominantly in terms of the firmware. We needed to have some extra monitoring to monitor the power, and then we exchange the information through SM bus. The blade management controller talks to the IAM controller over the I2C bus and the usual stuff. So when we start thinking about the implementation, there's a bunch of open questions. The first one having to do with what is the power budget that we choose? What's the value that we need to have? There's a very interesting question about the enforcement strictness. And this has to do with whether are you provisioning the power from a power delivery point of view, which basically means there's a fuse that blows if the current exceeds that particular thing, in which case you want to be very strict about it. Or are you provisioning from a thermal point of view, which basically means that you're allowed a few occasional transients that exceed your power budget, as long as you guarantee that your heat doesn't exceed that. So that actually makes life a little bit easier, because you have relaxed enforcement constraints. And then finally, in terms of the power monitoring and control, should you be monitoring power or temperature? Should you be monitoring the individual components? Do you do polling, interrupts? How do you tie it back with P states? The usual kind of stuff. And then finally, in terms of the policy space, there's a whole bunch of policies. How do you assign power budgets? And there's two broad categories that I'm going to focus on. One is called preemptive, and the other is called reactive. And then so reactive is fairly straightforward. You let every server spend its power budget, and then there's an enclosure which adds up all of those. And if it turns out that you violate your total, then you kind of go back and knock people on the head and say, you throttle your power, and so on. So basically, the nice thing with the reactive system is you basically use as much as you want until told you cannot. And so the idea is you are always guaranteed one violation before you bring down the power. But the good news is basically that you don't really compromise performance, because you can be pretty aggressive. The preemptive is the other option, where you basically need to ask before you can use more power. Every blade registers with the central guy, and the central guy doles out a certain power budget, and the individual guys are guaranteed not to exceed that power budget. And then if you need more, you come back and ask more, and so on. And so the nice thing with preemptive is you're guaranteed never to exceed your power budget, but you have the overhead of having to go ask before you do that. And so there's some extra conservativeness in terms of the performance assumptions. So finally, there's a bunch of other choices. What servers do you throttle, and when do you unthrottle them? What policies do you use there? What level do you throttle them to? So we have multiple P states. So how many people here know of P states? Okay, about 5. So P states are basically defined by a standard called ACPI, and just think of them as multiple power performance states for now. And the idea is basically you can go from the highest performance, highest power state all the way to the lowest performance, lowest power state, or you could kind of look at intermediate points. And so do you do it incrementally, or do you do it really deep? So there's a bunch of open questions there. And finally, as with any other heuristic, you have resource estimation and polling, and how often do you do that? And there's a whole bunch of things you can do there.
Can I ask you a question real quick before you jump off that slide? For the preemptive one, where you ask before you use more power, how do you handle boot before really complex logic is in play here?
They always start off with the most conservative thing. So basically, remember in the picture I showed you that there is changes in your blade firmware, and there's actually a lot of post power on self-test stuff that we do. And so there's also, that is easy, but the more interesting thing is what happens if the controller dies. And then how do these blades all go to their respective stuff? So there's a whole bunch of logic around heartbeat checking. And so for those kind of events, we go to very conservative assumptions till we vote and figure out a new checker. But so
you're just careful to start in a really high P state. And
exactly. And that's why we need the firmware support, because you really, you could run Windows or you could run something else. And so we need to kind of make sure that this happens at a level that we control and we can guarantee. Otherwise, like he pointed out, we'll have things melting, and we really don't want them to. Yes, sir.
Question of clarification. So this scheme actually doesn't save power, it just saves the provisioning for power. Is that correct?
Correct. So what we're trying to do is throttle the peak. Remember, again, that's why I mentioned what I'm trying to give you is a flavor for both the average and the peak power and how they differ. But you're absolutely right. So, and as far as the details about the power on self-test, the boot, the heartbeat, the paper has a lot more details. So you can look at that. So, and if you can't find it, send me an email. I should be able to get you that. Okay, so a quick evaluation. So we actually built a prototype. We used transmitter blades because that actually has support for P-states which are across the space. And then we made the changes for the power monitoring. We ran a bunch of different benchmarks. We replayed all our enterprise workloads. That's easy. And then we ran some real workloads as well. And we measured power and performance. And there's a bunch of trade-offs in terms of the various models here. We also built a pretty elaborate simulator, which also makes for some very nice demos that I may not have time to go into. And so with the simulator, we actually looked at about 70 different metrics, evaluating all sorts of possible per blade summaries, enclosure summaries, per blade summaries during peak, and so on. So as I go through the results, you're going to have questions, and I'm going to invoke some of those. Anyway, so the high-level results, basically here are our, these are simulation results. Here are our 9 enterprise sites. The enclosure was rated at 500 watts. We brought the provisioning down to 400, 425, 450. So anywhere from about 10 to 20% savings. And so this is the loss in performance. And so essentially you can see that the loss in performance is 0 in the reactive case and then close to about 1 to 5% in the preemptive case. So the point is you can bring down your power budget by 20% without really compromising anything there. So why is this low? The main point is the only hook we had for power control is the processor, and that is actually at anywhere from 25 to 50%. And so we actually bring down the processor quite a bit. It's just that if you look at the blades that we have, the processor is about 50% of the total power. The memory actually takes quite a bit, and we didn't have support for memory power states in this particular prototype. But you could very well start thinking about doing the same thing for memory as well. And then there's an enclosure level amortization as well. So the point again is marginal impact on performance. And again, this was kind of interesting because the preemptive is actually quite competitive to reactive, and we didn't really anticipate that when we started doing these experiments. And it turned out basically you could, as long as the communication overhead wasn't too bad and you did that fast enough, it's not such a big deal. Yes, sir?
That last question, though, is really kind of important, isn't it? That the cost of running a data center is really the power I consume, not the power I provision to consume.
Yes and no, because if you over provision, those power supplies are running inefficiently at, if the power supplies typically are most efficient when they're running at 90% of their capacity, 90 to 100%. If you over provision and you run those things down, they're consuming more energy in the power. So there is an energy savings by having
but an alternative approach said, if suppose I could get twice as many CPUs that were slower versus half as many that are faster, there might be much larger savings there.
Right. So there are two ways to answer this question, right? One is the way that he answered it, which is basically, even though it's a provisioning issue, the provisioning also determines your OPEX. And in fact, there is a data center in San Francisco that I went to, and I said, what happens if you turn 90% of your servers? 90% of your servers are turned off or they're idle. What would happen to your electricity costs? Because he was griping about how big his electricity costs were. And then he mentioned the electricity costs would go down by only about 20%. And it turns out it's exactly what he said, which is you bring down the servers, but you now operate your power supply at a very inefficient point in this efficiency curve, and the power supply ends up wasting more energy. So there's an issue with provisioning from an efficiency of operational point perspective, which is kind of a second-order effect. Going back to the first question that you asked, we actually have a pretty elaborate equation. If you go to my website, there is a tech report on the TCO model for a data center. And if you look at the total cost of a data center, there is the CapEx cost, which is the provisioning. How much power supply do you provision? How much power supply how much cooling do you provision, and so on. And then there is the OPEX cap, which is the average power. And the CapEx costs are also quite big, especially when you go to denser and denser blade servers. You're looking at 55 kilowatt racks or 80 kilowatt racks, which is unheard of. And you start thinking about the CapEx provisioning to cool those things. You're starting to think about liquid cooling. So HP has a solution called modular cooling, which is essentially two liquid-cooled side racks on top of your main rack. And so there's a whole bunch of elaborate solutions, each of which comes with cost. And if I can provide guarantees that your peak power will not exceed a certain point, you can pretty dramatically reduce the CapEx cost as well. So think CapEx and OpEx, and your question basically translates to, is CapEx cost a significant fraction of total cost? And the answer is yes in those cases, right? Still don't sound convinced. I'll come back to you in a minute. So, okay, so this was basically just the utilization traces from the past. We had all the various errors there, so the goal was fine. The point again is these were, we replayed utilization traces, but one would argue what happens to real workloads. So this is actually a desktop application basically being played back in back-end servers, so kind of like the consolidated client infrastructure, the Sunray servers. And the point was basically, the goal was, just looking at throughput doesn't really help you if during your most critical point you ended up throttling. So for example, with the desktop users, I click on a Windows Explorer icon, and if it takes 10 seconds to pop up instead of 1 second, that is not very nice. And you could still get good throughput, but you kind of messed up in the most important areas. And so this is actually a VNC desktop playback. And what these two lines, which almost overlap with each other, are the normalized response times for the various events. So basically, the VNC play is a benchmark suite from Stanford, and it measures the response time from a user event, like a click or a keyboard, to when the actual thing happened. And the point, again, is that our algorithms are pretty sensitive to these kind of things, and you can actually not screw up too much. We did a whole bunch of sensitivity experiments, and the point, again, is the benefits from this approach depend a lot on concurrency. So if you have all the workloads going at 100% utilization all the time, this isn't the right approach for you. And this picture just illustrates that. I have a simulator demo that I'm not going to go into. And one of the things that's interesting is I talked about peak power provisioning, but there's a bunch of other interesting benefits as well. And one of the things I talked about is even though we look at an enclosure, there's cascading benefits beyond the enclosure at the rack, at the data center level, and so on. The second interesting aspect is this approach for the first time now makes the power budget happen at the software level. And that's very interesting for a bunch of reasons. So let me give you an example, right? So if you're looking at designing a 500-watt enclosure, the way blade designers would do it right now, and that's the way we do it as well, is basically you take your 500 watt, you kind of divide it by 20 blades, and you say, well, each blade is going to be 25 watts. And then you take an individual blade and you say, well, that means my processor power budget is going to be 15 watts. And then you go to Intel or AMD and ask for a 15-watt power budget. And usually what Intel does is they're going to look at their bins, and they're going to say, 15 watt just falls into the low power bin, and we're going to need to use ultra low voltage technology, so I'm going to charge you an X% premium over something that would have been much more cheaper if you had asked for a 17 watt thing, right? But the nice thing with being able to do the power budget at the software level is basically that you don't need to worry about those anymore. So I can still design a 25 watt blade, but I can have like a 17 watt processor because I now enforce the power budget in software. And that gets to be very interesting because I have some very interesting cost dynamics to that, like I talked about. So again, I don't have time to go into this in detail, but as you think about it, it's going to get clearer. The other nice thing is now I can vary this power budget on the fly. So for instance, this ties in with some of the other optimizations I'm going to talk about. If I have data center cooling that I can redirect on the fly, I can adaptively vary the power budget in some very interesting ways. And actually, so suppose you have a peak power budget and somebody moved a huge amount of cooling into your data center for 2 days, I can actually make my power budget higher and get some performance boosts and so on. So that's very interesting. And then finally, the same approach can be used for average power reduction as well. And then we can talk about that. So the point is basically, if you look at peak power in ensemble level, by being able to look at a collection of systems and being able to manage the power at a software level across the common case instead of this usually rare nameplate cases, you can get quite a bit of power savings. And as before, you need some intelligent heuristics to make sure that this doesn't get out of control. And then so if you read our paper, we can talk more about what this does. Okay, so it's 11:30 now, so I'm guessing I'm between people and lunch. So I'm not going to be offended if people leave. I'm just going to continue going through that. I have probably about 10 minutes more of material. And so what I really want to do is to quickly tie it in with some of the other contributions there. So one of the pieces of work we did is to look at heterogeneity. And so the idea behind heterogeneity, I believe Rakesh was here and he gave a talk. So this was work done with Rakesh for his thesis. And the idea was basically you have a multi-core architecture, what happens when you have asymmetric multi-cores. And this was proposed in 2003, and the industry has since moved to adopt asymmetry in some interesting ways. Intel, AMD, and IBM have all kind of expressed interest in having these things. And the point was that we showed that heterogeneous multi-cores can actually get you some pretty dramatic power savings, and we also showed that it can get you some pretty interesting performance savings for a given area as well. What Rakesh probably didn't talk about is that we've also looked at heterogeneity in the context of a data center. And what these two pictures represent is, again, the Apache server from HP.com. One of them takes 10 watts and the other takes 100 watts, right? And if you stare at it enough and you look at the axis, this is 500 and this is 700. So this is obviously the 100-watt one and this is the 10-watt one. But the point is, for a given set of load, maybe if I draw a line somewhere around here, I could very well take my 10-watt system and get the same kind of SLA guarantees that I would have on my 100-watt system, except that I now saved a 10x in power. And again, this has to do with the power efficiency, the MIPS per watt, the inflection point across various servers, and so on. And this picture actually shows the typical heterogeneity that you're going to find in any data center. And I bet, I haven't done this for Microsoft, but I bet there's going to be, most data centers, by virtue of the refresh cycles and so on, are going to have some inherent heterogeneity. And you could use that to get some pretty dramatic average power reductions. So, finally, we have a whole stream of research on what we call integrated IT facilities resource management. And one of the most interesting things there is a paper we published in Usenix last year. That should be Usenix 5. And this has to do with the idea of temperature-aware resource scheduling. So if you think about a typical data center or any typical cooled area, by virtue of the way you place your cooling, there are going to be some locations that are going to be hotter, and there are going to be some locations that are cooler. And so what we did in this research was to say, can I match my workloads in a way that the hot workloads go to the cooler locations? So think of the analogy as you have two rooms in your house and you're holding a party, and one room has an air conditioner. Would you rather move all the people to the room with the air conditioner and turn it down, or are you going to have people in the second room and blow air all the way across, right? And so that's kind of the analogy here. And it turned out that it sounds like a very straightforward idea. We thought, just go change LSF scheduler or your SunGrid scheduler, or just move workloads to what we think are the hotspots. It turns out that's the first algorithm here. Here is your analog temperature distribution. You want to match heat to do that. There's an interesting problem with discretization, because every server can go to one of 3 power states. And so even though you have this, you have to kind of discretize it to match that, and you get some savings there. But it also turns out that in a typical data center, there are some very non-intuitive heat flow patterns. This picture shows that. So each line here is a rack. And what we have here is, if I add a certain amount of heat, 1.35 kilowatts of heat, you notice that 2 other racks which are quite far away increase in temperature by 1 degree. And that has to do with how the airflow mixes, the entrainment, the short circuiting that happens in airflow, and so on. So the first algorithm was basically saying, this location is hot, therefore this location is bad. And the second algorithm says, this location is hot, therefore I'm not going to put workloads on that location. So there was some interesting causalities that we had to factor in. But the net is, by being able to come up with intelligent algorithms, you could save about 50% in energy. So, and going back to the Google data center, we are talking about, again, hundreds of millions of dollars purely through software optimizations to move workloads that are energy matched, that are cooling matched. And obviously, this picture here shows that this is valid only when the data center is not fully utilized. If you have a data center that's 100% utilized, you really have no choice in how you move this. But most data centers, including the Microsoft data center, is used between 20 to 30, 40%. And so this would be in this range where you can get some pretty good savings there. One of the nice things with temperature-aware scheduling is you can now think about this as a reliability play as well. So this picture shows a data center where this air conditioner has failed. And you see a whole bunch of red spots here which talk about how many servers die. And in fact, in this particular model, I believe within 90 seconds, about 180 servers are going to have thermal failover because of how this failure model is set up. And the nice thing with temperature-aware scheduling is I can automatically respond to these in much faster ways than I can if I had mechanical actuation. And I can move the workloads around in intelligent ways And between this and this, I believe, compared to the 180-odd servers that died, this had only about 5 servers that died. And so essentially, you can do temperature-aware scheduling to recover from failures. And this ties in with a concept that we've been working on called smart redundancy, where you really don't have to invest in the OPEX costs of having multiple air conditioners, multiple redundant solutions, but you can leverage your IT-level solutions to provide smart redundancy at the facilities level. And this is, again, very powerful and something that a lot of data centers have benefited from. Finally, there's a very interesting problem in terms of some of the work we are doing here, and I call this the intersecting control loop problem. And the problem is fairly straightforward, right? And I'm going to talk about this in the context of power, but we are really solving it at the whole data center for everything. So if you look at power, there is a power management loop at the processor level. For example, Foxton does power management across multiple cores. There's a processor level, there's a power management at the server level. Power regulator, which is a HP product, does something at the server level. There's something at the enclosure level, power balancer that we have published in ISCA. There is something at the rack and data center level. Again, there's several solutions that have been talked about. So there's going to be a control loop at the chip level, server level, enclosure level, data center level. There's going to be a control loop that's going to be looking at cooling. There's going to be something that's going to be looking at power. There's something that's going to be looking at performance. And cooling impacts power, power impacts performance, performance impacts cooling. There's going to be something at the operating system level. There's something that's going to be there at the distributed task scheduler level. There's something at the virtual machine level, vMotion talking about stuff. There's going to be something at the manageability level, OpenView, Tivoli, all that kind of stuff. And what ends up happening is that all of these are kind of looking at similar objective functions, or at least intersecting objective functions, and they often vary the same knobs, but there's really no coordination between those. And essentially, you have chaos in the data center as all of these different management optimizers, controllers try to kind of do things there. And so we have actually, I had an intern this summer who has come up with a very nice solution for this, where we talk about integrated IT facilities management, where you kind of provide it has a whole bunch of buzzwords here, holistic, multi-level, integrated. But the point is basically that you can coordinate all of these solutions and actually come up with something that works. And we found that actually her early results show that coordinating can actually get you much more power savings than not coordinating at much more higher safety guarantees. And finally, this is the work where we kind of talks about the taxonomy. I'm not going to really go into that. What I will point out is that at HP Labs, we spend a lot of time understanding the fundamental limits. I talk about 10x improvement, 100x improvement. How much should we declare victory at? And so what this is Feynman's equation for information transfer. It says that basically if you look at 1 watt, which is one handheld device, you can put about the computation worth of 1 billion Pentiums there. So we are obviously nowhere close to the theoretical limit. So we have a lot of work to do. But a more pragmatic way to look at it is basically the energy consumption. Somebody mentioned GSM versus 802.11 and so on. So we actually did this experiment where we ran the same exact task. We ran email application running on Linux across a laptop, a handheld, a cell phone, and a RIM pager. So same exact application. One takes 92 milliwatts. The cell phone takes 6 times, the handheld takes 10 times, the laptop takes 160 times this power. So what we have again is, what this says is, if I were running email on a laptop, I should be able to make it at least 100 times more efficient than what we are doing right now. So we have a gold standard that does it much better. So even if you forget about the billion Pentiums, we still have much more we should be doing and we can do. And then I have this very nice interface, the definition of taxonomies. And the context for this is basically having looked at power management all the way from handhelds to data centers, chips to servers. It's pretty much the same set of fundamental problems. And I kind of joke that this is your recipe for improving power in any system that you have. And so I'm not going to go into more detail. You got to read my book to find out more about it. So a quick note on the tools. We have a lot of work here. There's something we published a while back on energy monitoring and measurement. And the idea is, wouldn't it be really nice if I could draw a pie chart, just like what gprof does, but this pie chart tells you where you spend your energy from a software stack. And it turns out it's relatively straightforward to do, and it's relatively powerful as well. So that's the first bullet here. We have a paper published on Splice, and it turns out when you're trying to correlate data across the IT and facilities domain, it's a very challenging problem. And we have the very first what we call the extended knowledge plane that does that, and we have it deployed in our data center, and it's been generating a whole bunch of insights there. Finally, in collaboration with several people at Stanford, we've been looking at this notion of proxy-based environmental metrics. So how is the operating system going to understand how much power is consumed? And we actually have a paper that's going to come out in the end of this year where the operating system, purely based on OS level metrics, I can get a power model that is within about 5% accuracy of an ammeter that you insert in every server. So when you think about a data center with thousands of servers, putting an ammeter at every server and making sure they're all synchronized and they all talk to each other is a pain in the neck. But now if you have things at the operating system level, within 5% accuracy, I can do some very interesting things. And I can now tie it into controller optimizations, which say the operating system, when it's doing scheduling for power, it can now evaluate various options. So there's a whole bunch of stuff there. We are also working on this notion of benchmarking. I talked about our work with the Department of Energy in terms of energy-aware metrics. And the initial metric that was very simplistic that the folks there were considering was something around MIPS per watt. And very soon it was clear that that wasn't the right metric, and we've been working with them on several metrics. And in fact, HP has a proposal under review right now called scale-down efficiency that builds on some of the work we talked about here. But we are also looking at several different ways of benchmarking energy, comparing different systems, different ecosystems from an energy efficiency point of view. Anyway, so I did zip through a lot of that in the end. But the point again is, irrespective of what you're working on, whether you're working on processors, operating systems, data centers, handhelds, enterprises, it's obvious that energy is going to become one of the most important things, and power is going to become one of the most important things. And what we have been doing at HP Labs at the SmartPower project is to systematically address inefficiencies. And I kind of talked about the suite of solutions we have and the various tools that we have developed. As I mentioned, even though we've been focused predominantly on power, a lot of the insights scale much beyond power into broader resource design, management, and monitoring. And at the end of the day, power is one element of the TCO. I mentioned the tech report on TCO that we have. And so the whole goal is to start looking at TCO and cost of ownership. And then when I give my Blades++ talk at some point, you can see how a lot of this ties into looking at TCO and end-user experience in some very interesting ways. Any last questions?
You mentioned how power is distributed between processor and memory. Now, processors are also mainly memory, known as cache. And if you had to design for bang for the watt, what would you do to the cache hierarchy?
Correct. So, and there's tons of academic literature there. And if you look at some of Intel's roadmap, it is starting to get there, right? I mean, in fact, a lot of our research is now looking at memory power as well, because the processor power, there's a lot of low-hanging fruit with P-states, with better design that we can get there. But at the end of the day, I mean, you're just doing more work. You're putting 32 cores in a processor. I mean, that's why I like to put back Feynman's equation there. You want to do some work, you have to burn some energy, right? So you're not going to get around that. Then it goes back to your question of, is it better to burn that energy across a distributed system? Can I have 10 racks in a big room versus having 10 blades in a small enclosure? And then it goes back to the manageability space issues there. So absolutely. So cache is very important, and I think it will get solved in the next year or two. At least the Pareto will get solved.
Preliminary information on power management at the memory level? Anything promising?
Well, again, at the end of the day, remember, there's nothing new to invent in power management. It will be, you have a knob to bring it down. So if you look at DDR2, there's some very interesting power states there. So we have a paper coming up that I can send you a preprint of, which talks about some of those.
Thankfully, nothing runs at nameplate.
Thankfully.
The diversity has been my saving grace in trying to keep labs cool, right? Because, people put in a box with a nameplate of 300 watts and it draws 100. So there's this over-provisioning keeps going on, and I'm not sure. I can give you an example of efficiencies. And we have groups that are investing in rackables, because they want the super high density. But one of the things, so I said, well, okay, what's a rackable? I went out researching our site. One of the things they do is they match the power supply to the actual demand that a box is going to see, and it's just the box is what it is. And I know most of the OEMs size the power supply on a server box to, okay, what's the most somebody could possibly stick inside this box? And so you end up with a power supply at 500 watts on a machine that's going to draw 100. And an example of how power supply efficiency can help. So on a single-sided rackable rack, it draws 6 kW. On their two-sided rackable rack, they put in a single large DC power supply that feeds all the it draws 12. It draws 10. So instead of being double, instead of going from 6 to 12, it goes from 6 to 10 when you double it. So there's a lot of low-hanging fruit in the area of power supply design that could be even without getting into the software management piece, it would just enhance that.
Sure, fair enough. I mean, and there's tons of work there. If you look at the power supply efficiencies over the past, let's say, 5 years, efficiencies have gone up pretty dramatically. In fact, the Energy Star rating, they started off saying the first thing we're going to legislate is to look at power supply efficiencies, and we're going to insist that every server comes with a power supply efficiency that's over a certain range. And very soon they found out that people have improved the heck out of that. So, but there is definitely low-hanging fruit, and I think most of the roadmaps account for that. What is interesting is tying that in dynamically to the load, because again there's an efficiency curve, and you have two options. One is to make the efficiency curve, stretch it out so that it's more efficient, and that, from what I understand from the power supply guys, is a very hard problem. And so we've looked at some interesting ways there. So we have some intellectual property that captures that. So I guess your point is well taken. There is low-hanging fruit in power supplies. I think some of that low-hanging fruit will be harvested in the next year or two. There is going to be other stuff, and there are going to be other business reasons for why that's not done.
I wanted to ask if you, in your research, when you're working on reducing power for display, did you ever look at the research that's going on with regards to fuzzing the area that's out of focus, and, for example, turning off pixels randomly in the area that's not in the focus?
Yeah, we did do that. I mean, the optimizations I showed you was where we dimmed every pixel, and then we actually fudge around where we say we kind of dim every 13th pixel and then randomly change it and hope nobody really notices. And it turns out people notice because people's peripheral visions are tuned to all these subconscious things. So, and as I said, I mean, you could kind of dim everything in fairly honest ways and still get all the benefits and still have the users say that they like the interface. So we didn't go down that path, but we actually have a bunch of algorithms in the patents about this approach which talk about doing some of those things.
So you're saying the user response wasn't really well?
We didn't look at it in great detail, but the few things we did, even I could notice it. And my first rule of thumb is I need to enjoy my interface first before I even ship it on somebody else, right? And so we really didn't go down that path further. We had, I think, in one of our experiments, we had one interface where we looked at that. And the Kodak guys were very interested in this because with OLEDs, there's value in doing this because of the lifetime for a bunch of reasons. But so, like I said, the straight answer is we really didn't spend too much time thinking about it because it didn't seem worthwhile to go down that direction. Sounds good. There's nobody left to clap, but
appreciate it.